Now we're going to use the interior product, just a very simple case of it, just a vector acting on a 2 form, to wrap up our whirlwind tour of how differential forms let us restate all of electrodynamics, or at least the core facts of electrodynamics. So we have this 2 form F, the Faraday 2 form, which incorporates the E and B fields. And how does that actually do anything? We've seen that the Maxwell's equations, which relate E and B to each other and talk about how the fields evolve in time and how they're created from charges and currents, we've seen how those really get encapsulated beautifully in forms. But what about the Lorentz force law, the law that combines, well, there's really sort of 2 separate laws you get taught in basic E&M, which is the electric field acting on a charge and the magnetic field. And they act in very different ways, and we'll see that that's really natural coming out of this field 2 form. So we do have to combine, as we did here, we have to combine space and time. And so what we have to do is we have to look at a particle. Let's say it has charge q and mass m. We won't use the mass much, but it's nice to have a mass for it. Let's say it's moving in space with a ordinary velocity, 3-dimensional vector, v1, v2, v3. And because I've never done anything else in these videos, we're going to work in units where the speed of light is equal to 1. So if these numbers actually going to be dimensionless numbers, just expressed in terms of units of c, the speed of light. And if they're very small, then we're in a case where hopefully the relativistic effects that we might expect will be small. So I am going to introduce a tiny bit of relativity here, just so that we can actually have an honest, correct definition of what's called the 4 velocity, which I've started a picture for over here. And so here's the idea. Let's go over to the picture. I've got just one space dimension drawn and one time dimension. So you really want to think of this as incorporating all 3 space dimensions, or however many you want, really. It doesn't actually matter for this stuff. And so we, as is our standard, a very standard convention in relativity, we're putting the t actually up vertically, and the time is vertical and the space is horizontal. So if I've got a particle moving, then it's going to be like along this line. It's going to be moving in space, but it's also, its clock is ticking. It's going to be moving in time as well. So all the different events in the world line, or the history of the particle, are going to be this dotted line. And let's say this is a vector. That's supposed to express its velocity both in space and time. Its motion through space and also the clock ticking as it's moving through time. And it would make sense probably to define the 4 velocity as something which just has the components v1, v2, v3, and then for this one it should just be, for this, v1 is how much space, how much of the x1 coordinate has been traversed in 1 click of the clock. So this one, it seems like maybe should just be the number 1, because it seems like in 1 click of the clock I've gone 1 time unit, and so this would just be sort of dt over dt is equal to 1. Now it turns out that that's crucially wrong in relativity. And just briefly, it's because there's a notion of how fast your personal clock ticks, called proper time, which says how long did you experience this time, and that's not equal to what an outside observer building a coordinate system would say is how long their clock ran. The relativity of time measurements is one of the most fundamental, weird, and unexpected things about relativity, but it's basic to the universe. Turns out that there's a very simple fix for that, and it also affects the v1, v2, and v3 coordinates. It's to multiply this whole thing by a number gamma, where gamma is 1 over the square root of 1 minus v squared. If we put back in the c's, it's v squared over c squared there. And so what you can see is that if v is a small percentage of c, or in other words, my dimensionless v is a small number, this is small, this is close to 1, this whole thing is very close to 1. And that's why Newton never noticed this. And nobody before the late 1800s noticed this, is that this gamma factor is almost always very, very close to 1 for sort of terrestrial ordinary particles, unless they're in particle accelerators or something like that. Okay. But so this is what we're going to use, and in fact, we'll leave the gamma in for a little bit, but we'll actually, to get some connections to sort of what we're familiar with in physics, I'm assuming you don't know relativity, eventually we're just going to set gamma equal 1. Okay, so it's not really going to bother us too much, but I wanted to make sure I actually gave you the real definition in case you want to continue with this. And who knows, I might make videos about relativity at some point soon anyway. Okay, so this here is just my explanation of just what I was talking about here. And here's what we want to do. what we're going to use is the interior product. We're going to take that 4 velocity, so this is going to be the 4 velocity, we'll call that u, and we're going to take the interior product of that with the 2 form. Multiply it by the charge, and the way I have things set up, I need a minus sign, and it turns out that that basically is going to be the process that creates how the fields act on that particle that's moving with that 4 velocity. Okay, so let's look at how that works. We're going to be taking this, well, I don't need the equals really. We're going to be taking this quantity, well, let's get the whole thing down. And as usual, I have this pre-prepared as well. Okay. So let's see, let's take IUF. That's going to be, we're going to put an IU in everything, because remember it's linear. IU, ooh, not a capital though. I've got caps lock on for some reason. There we go. Okay, so we're going to take IU of this. Oops, sorry. And we're going to take IU and act that on this. Oh, and it's parentheses, of course. Etc. I'm not even going to write the whole thing out because I have it pre-prepared. The main thing is you can do it yourself if you want. Let me scooch this a lot wider because we're going to have some big expressions here. You could do this yourself if you want, if you've seen the other video where we figured out how to take the interior product of a random vector with a 2 form. And it wasn't super complicated. So I'll even show you where it is. It was up here. IU on dx wedge dj. It's just this. You get the corresponding components and wedged with the other dx's and with a minus sign, something that's sort of vaguely like cross product maybe, and we're going to see that it exactly is going to lead to a cross product when we make this sort of more pedestrian. Okay, so let's go ahead and just replace that with the real version. That's my last pre-prepared thingy down here. And we're going to see how that works. So, boom. Okay. Woo, I need to make it even a little wider. Okay. So, first of all, I distributed in the minus sign. And so the E's were negative and the B's were positive, and I just switched the signs. So the IU on dx naught wedge dx1 just gives you u naught dx1 minus u1 dx naught. IU acting on dx naught dx2 just gives me a very similar combination with the 0s and 2s. Here it's 0s and 3s, 2s and 3s, 3s and 1s, 1s and 2s. Okay. You might want to pause, and I'm going to go on, but you might want to pause and just actually either do it yourself or really make sure that take one of these terms and really convince yourself that the signs are right, the 3s or 1s are right. Okay. Now, each of these u's, remember u naught is gamma, and then the u1 is like gamma v1, u2 is gamma v2, u3 is gamma v2. So everything has a factor of gamma, which I've pulled out here. And then what do we get? I wanted to figure out, I want to collect together everything, just very basic stuff. dx naught, what's in front of that? dx1, what's in front of that? Okay, dx naught, well, I see an E1 U1, which is a gamma E1 V1. Okay, that's the ordinary velocity in the x1 direction, multiplied by E1. Similarly, a dx naught, you get an E2, and there's a V2 once you take out the gamma. Okay, and an E3 V3. Interesting, you might want to think about that for a sec. Hey, does that look familiar? Okay, that's in front of the dx naught, and we might expect that to be a little special because that's the time component. We weren't maybe necessarily expecting to get anything there, but we'll see. It's cool. Now what else? Let's see. Well, the dx1, there's an E1 times U naught. That's just gamma times 1. So once I factor out the gamma, it's just E1. Okay. And what about the dx2? That has an E2 U naught, which is just basically an E2. Then an E3 coming in here. The more interesting stuff with the space components, like dx1, for example, that has a minus B2U3. That's right. Right there I switched the order a little bit and made it a V by bringing out the gamma. And what's the other dx1? It's a plus U2 or V2 once I take out the gamma times B3. And that's this guy. Similarly for these two guys. All right. So let's see what's up with that. Now, let's put the Q in as well. Okay. Equals. Okay, so I claim the claim was that we're going to get something very interesting if we express that as the tilde of a 4-vector W. So let's just write down this equals W and then tilde it. Well, where W equals what? Well, what's going to be the first component? Well, Remember, when you tilde in space-time, you have a minus. Oh, hey, there was a minus conveniently there to be waiting to be killed. Okay, and so that's going to be gamma. I don't need bold. Let me just scooch this up for a second here. With my recording, it doesn't work very well. Okay, try not to do that again. Oh. Okay, so W equals gamma times the first component. Well, what is this? This is E dot V. So this is just E dot V, where that's the ordinary three-dimensional vector, and that's the ordinary three-dimensional velocity, plus, let me bold that. Okay. Plus, and that's in the time component. Let me just put this in parentheses. So that's the time component, comma. Now what about the space stuff? I've got E1, E2, E3, dx1, dx2, dx3. That's just the vector E. So I'm going to put all the space components together. I've done this sometimes, where I have the time thing, and then just that's a number, and then the rest is going to be a three-dimensional vector. Plus, and what is this? This is exactly, if this is the first, second, and third components of a vector, this is exactly just the cross product. This is just V cross B. And so it's just E plus V cross, where's my cross? It's in here somewhere. Yeah, cross B. Okay. That's really, really cool. Oh, and then Q. Sorry, there's a Q here. So I'm going to put a Q there, and a Q there, and a Q there, and I don't really need those to be bold. I'm not going to worry about it. Okay. So what have we got? The space components automatically give us the force exerted by the electric and magnetic fields together on this particle. When I have a charge Q, by definition, the E field acts with a force QE, and the B field acts in this strange way, QV cross B. And so that cross product automatically is coming out of the interior product in the space components. Okay, so that's what this next question was about. Okay, if we just set gamma equal 1, just kill off the gammas. Oh, I didn't even put a gamma in there. Sorry, the real version was there's a gamma in front of everything. There we go. Okay. If I then just kill it back off, by assuming we're not in a sort of relativistic mode, then the space components is exactly the force. So that's what I was asking here. Do the space components of W look familiar? They are calculating the force on the particle from both electric and magnetic fields. And so that's beautiful that this Faraday 2 form, and then just put in with this four-dimensional velocity, automatically pops that out. But we get a bonus too. That's the space component. That makes sense for a spatial force. Well, what is this extra thing calculating? What would that calculate? Okay. Well, again, just set gamma equals 1 for simplicity, not to get too weird about relativity. QE dot V. QE, again, that's the force due to electricity. And if I take a force dot a velocity, think about that for a second, what that calculates. That calculates the power input to the particle by the E field, but remember the B field doesn't input any power because the force is perpendicular to the velocity. So it's still by both fields. Okay, it's just that the B field never actually does anything. Or in other words, it's the time rate of change of the energy of the particle. Well, that's really cool, because if we go back here, force, this is equal to the time rate of change of the momentum of the particle. And that's very interesting. That actually tells us something it gives us a hint about something about relativity. What we're getting is that this W vector, this four-dimensional vector, is equal to, in the time component, it's dE dt, and in the three space components, it's dP dt. And let's bold that guy. Huh. Okay. So in other words, it's d by dt of a combination called energy momentum. And so this is suggesting strongly that in space-time, we should put energy and momentum together as one object, with energy being the time component and the momentum being the space components. And that's exactly true. That's an incredibly important, useful thing to do. It's really sort of the key to relativistic dynamics, that energy and momentum get combined into the energy momentum 4 vector. And this, just this one calculation gives us this big hint that that's a great idea. Okay.